let's go over the classical circuits. And, well, NAND is universal. Actually, this isn't quite true, because NAND plus fan-out is universal, but fan-out is usually taken for free in classical circuits. So when people are designing chips for CMOS, what basic gates do they use? Anybody? Yeah?
NAND, NOR, and NOT.
Yeah. CMOS, NAND, NOR, and NOT. So any idea why? Yeah?
It's easier to build that out of transistors than to put, like, that's what naturally comes out when you just have like 2 transistors maybe. And then to make an AND, you'd have to invert that, so it's just.
Yeah, well, you can make a NOT, make an AND by using a NAND followed by a NOT. And that is, well, so AND is more complicated to build than NAND. So you might as well just stick with these 3, I think. But you don't want to use just NAND, because then you would have to work hard to get NOR and NOT. And you don't want to work hard. You want to choose a set of gates and the universal basis that is as easy as possible. So quantum circuits. Universal gates. Okay. So we're going to build a quantum circuit out of some set of universal gates. And the universal gates we choose, well, all 2-qubit gates. So I think this is what we're going to prove is universal today. C0, all 1-qubit gates. And C0, H, X, Y, Z, T, and S gates. And people should remember what H, X, Y, and Z gates are. So let me remind you what S is and what T is. S equals 1, 0, 0, I, and T is equal to 1, 0, 0, e to the pi I over 4, and T squared equals S. So this is a universal set of gates. And of course, it's not the smallest universal set of gates, because X can be HX, Z is HXH, etc. But this is the universal set of gates used by Nielsen and Chuang in the book. And it's a reasonably good set of gates. When you actually go to build a quantum computer, you may not use the set of gates, because maybe there will be other gates which are much easier to implement, because you have much more freedom choosing which gates to use in a quantum computer than you do in a classical computer. So I want to give a proof that these are proof 2-qubit gates are universal. And actually, I should put a caveat to this statement. C0, H, X, X, Y, Z, T, S cannot produce all gates. Can anyone give a reason why this is true? Produce all quantum gates. Yeah, I think they can produce all quantum gates. Quantum unitary gates. Yeah?
Well, you can't do any phase shifts other than by multiples of pi over 4.
But you can. Because what you can do is you can, with C naughts and H and these, you can get a lot of different phase shifts. Yeah?
I was just going to basically say the same thing.
Okay.
You can't do arbitrary phase shifts.
Okay. How many circuits can you build out of these gates? Countable number of circuits and uncountable number of gates. Because, well, because there are continuous variables in here, which is an uncountable number, and there's a countable number of circuits. Yeah?
Does it mean anything to say that you can approximate any, you can approximate an uncountable number of gates with a countable number of circuits?
Yeah. Right. But you can get arbitrarily close to any gate. And in fact, you can get arbitrarily close to any gate with a reasonable number of a circuit of reasonable size of these, where you need to define what reasonable is, but it's polynomial in the error you want. So, but we won't, and that's called the Solovay-Kitaev theorem. It's not easy to prove, and we're not going to prove this. But so this is actually good enough.